Welcome to Signals and System subject classes. Now we are going to start the fifth chapter, that is continuous time Fourier transform. In the previous class, we finished the fourth chapter, that is discrete time Fourier series. So what is the purpose of the Fourier transform? In this subject, the main concept is converting the signal from the time domain to the frequency domain. That is the main concept. So in Fourier series also, it is a conversion from the time to the time to the frequency and frequency to time domain. So this is the Fourier series. In Fourier series, we can convert the time to frequency, but there is a condition: the signal must be periodic. But in continuous time Fourier transform, we can convert the signal from the time domain to the frequency domain for the up period signal. That is the advantage of the Fourier transform to the Fourier series. Then we go for the how to find the conversion signal in frequency domain and signal in time domain whenever given signal in the frequency domain. So in the previous case, we have taken the period signal. Now we should change the that Fourier series representation to the Fourier transform. So in continuous time Fourier series, so here I'm writing the continuous time Fourier series representation and its Fourier series coefficient. So one periodic signal, so periodic signal in time domain. So that is, so this is this wave, this symbol, it represented as periodic signal. So this continuous time Fourier series representation, so that equal to sigma ak into e power jk omega naught into t. So in continuous time Fourier series, AK is a periodic signal. It is not periodic. So the K must be from minus infinitive to the plus infinitive. So its Fourier series coefficient formula. So AK that equal to 1 by T integral x of t. So it is a periodic signal. E power minus jk omega naught into t into dt. So we should do the integration. We have taken the periodic signal. So just we have to do the integration within the one time period. So the limits are minus t by 2 plus t by 2. Minus t by 2 plus t by 2. So that is the AK. So this is applicable for the periodic signal. So here I'm drawing one periodic signal. So one periodic signal. So this is the periodic signal. So this is pulse is repeating for every time period up to infinity. For the plus infinity, it goes to minus infinity. So for this case, So previously we have taken the Fourier series to convert the time to the frequency. Now we have to convert the signal from the time domain to the frequency domain for the aperiodic signal. So that aperiodic signal, so this is a periodic. So this is a aperiodic signal. So in this aperiodic, it has only one pulse. So now this is x of t. So this is the periodic signal. So this is periodic signal. Periodic. Now it is aperiodic signal. So a periodic signal, this is time period. So T capital T is a time period. Now we have to find the frequency signal for this x of t. So we need to change this Fourier series. These are the Fourier series representation. So Fourier series, continuous time Fourier series, continuous time Fourier series. We need to modify these equations. It becomes Fourier transform, continuous time Fourier transform. For that, now we need to derive the continuous time Fourier transform equations. Again, I'm going to write here these equations. So x of tau, so x of tau, so its Fourier series coefficient, Fourier series representation, ak into e power jk omega naught into t from k from minus infinity to the plus infinity. So its Fourier series coefficient ak equal to, so 1 by t time period, so integral, so minus t by 2 plus t by 2, t by 2 x of t e power minus jk omega naught into t into dt. So we are taking the x of t. This is the x of t signal. We are going to find this x of t. So this x of t, it is also we are assuming this is also we are assuming this periodic, the time period equal to infinity. The time period t equal to infinity. Is it? For that case, here I am writing the signal. So x of t. So this is x of t. So this is periodic. Assume we are assuming this is periodic within the this is time period. T1 to the minus T1 to the plus T1. Is it? this is x of t for mod t. So this is the half of t. T by 2, and this is minus t by 2. So it's left by 2. So this is 0 for outside of the interval. Outside. Outside of the interval. So the time period here, this time period equal to infinite. So now this aperiodic, we are assuming periodic with the time period equal to infinite. For the case, here I am writing ak equal to 1 by t integral minus t by 2, so plus t by 2. So within the this period in the interval, this x of t period signal, it becomes the x of t only. So x of t into e power minus jk omega naught into t into dt. So here the time period equal to infinitive. So now I'm substituting. So 1 by t integration minus infinite to the plus infinitive x of t into e power minus jk omega naught into t minus jk omega naught into t into dt. So the Fourier transform x of j omega. So this is the x of j omega. It's a Fourier transform notation that equal to minus infinity to plus infinity. X of t, we are taking here minus j. We are assuming k omega naught equal to omega frequency, angular frequency, that could dt. So what we have taken here, the ak here I have taken ak equal to so 1 by t into x of jk omega naught. Is it just k omega naught? Here we have taken the omega. So this is the Fourier transform formula. X of j omega equal to integral minus into plus infinity x of t e power minus j omega t dt. Now, so this is the Fourier transform. So we want to find the x of t. X of t, just substitute this ak value in this. So this is the Fourier transform formula. Now this ak substitute in this equation x of t, then x of t. So it is a periodic. So this the curved line, it represented for the periodic signal. So sigma. So ak value equal to 1 by t x of jk omega naught into e power jk omega naught into t from the k equal to minus infinite to plus infinite. We know that omega naught frequency equal to omega naught equal to 2 pi by t. So 1 by t equal to 1 by t equal to omega naught by 2 pi. So this x of t, so 1 by t, sorry, 1 by 2 pi, 1 by 2 pi sigma x of jk omega naught e power jk omega naught into omega naught. So this is the one function k minus infinity to plus infinite. So this is one function. This is the second function. So this is so multiplication between this function and this function. So x of t. So time domain equation x of tau x of t equal to 1 by 2 pi is equal to sigma x of jk omega naught into e power jk omega naught into t into omega naught. So multiplication between this function and this omega naught. K from the minus infinity to plus infinity. So it becomes, here I'm going to draw the waveform like this. So this omega versus, so x of, so omega x of j omega into e power j omega t. So for example, I'm assuming this function as, so here this value is, for example, this value equal to k into omega naught. So this value equal to k plus 1 into omega naught. Omega naught is a constant. So this k omega naught, this it is belongs to the omega variable. So for the corresponding k omega naught, so this is a magnitude of this magnitude equal to, so this is the magnitude for the k omega naught. So we can write this magnitude equal to x of jk omega naught into e power jk omega naught into t. So if you do the integration, you will get the x of t. So this is the multiplication between this function and this function, and addition for the based on the k values. Then we will get the this waveform. Is it? So if you do the multiplication and addition for the various k values, so we will get the x of t signal. So this x of t equal to, 1 by 2 pi. So the summation is equal to the integration between this function and this function with respect to this variable. If you do the integration minus infinity to the plus infinity, so that equal to x of j omega into e power j omega t into with respect to omega. So both are same. So this equation and this equation also same. So Fourier transform. So Fourier transform formulas are x of j omega equal to, so CT Fourier transform. So x of t is a signal in time domain. In frequency domain, in Fourier transform, it is must be denoted by the x of j omega. So x of j omega, equal to, already we have derived it in the previous slide. So that equal to integral of minus infinite to plus infinite, x of t into e power minus jk, sorry, omega t into d omega, sorry, dt. So this is dt. The corresponding signal in time domain x of t equal to 1 by 2 pi, so integral, so minus into plus infinite into x of j omega into e power j omega t into d omega. So similarly, we can write for the Fourier series also. So continuous time Fourier series. So continuous time Fourier series. So it's a Fourier series coefficient. It denoted by the AK. So that's AK formula. Fourier series coefficient AK formula, that equal to 1 by t minus t by 2 plus t by 2 within one time period. Why? Because here x of t is a periodic signal into e power minus jk omega naught. So omega naught is a constant here. This omega is a variable into dt. So for Fourier series representation means signal in the time domain, that is x of t ak into e power jk omega naught into t, k from the minus infinity to plus infinity. So this is a Fourier series. So this is about continuous time Fourier transform. The convergence of the Fourier transform. So convergence of the Fourier transform. So before applying the Fourier transform, it should satisfy the three conditions. The first condition, it should be integrable. The first condition is absolutely integrable. So x of t, absolutely integrable. So means integral means, so within the minus infinity to plus infinity, the mod of x of t finite value. The second one, it should have the maxima and minima within any finite interval. So x of t have a finite number of maxima and minima. within any time interval. Any time interval. The third one is discontinuous. It should have the finite number of discontinuities. So x of t have a finite number of within any time interval. So these are also called as Dirichlet conditions. So you should remember. So these are called. So note. So these are called as Dirichlet conditions. Simple thing. It must be absolute integrable. It should have the finite maximum, minima, and discontinuous. These three are very, very important in case of the Fourier series, and in case of the Fourier series within the time period. So here any time interval within. Then we go for the one problem. So here I'm taking one signal, continuous time signal. That is, this is the problem. So an x of t signal, a x of t signal that equal to e power minus EAT into E of t. Here A positive. So this signal is exponential decay signal. For this, we need to find the Fourier transform. So before that, I would like to draw the signal in time domain. So this is exponential decay signal. So exponential decay signal. So at t equal 0, this value equal to 1. But it touches the 0 at infinity. Up to infinity, it decreases up to. Is it? So this is the x of t. For this case, we have to find the Fourier transform. We know the formula, Fourier transform formula. It's very, very important for the Fourier transform. Everyone should remember this formula, x of j omega. So what x of t is given, we need to find x of j omega is what? So x of j omega, formula that equal to integral of So x of t into e power minus j omega t into dt from the minus infinite to the plus infinite. So the given signal x of t, it is having the magnitude for the positive values. U of t is multiplied. So it started. So it will have the magnitude from the 0 to infinite. Is it? Then so within the 0 to infinity, the x of t equal to e power minus at, the u of t equal to 1 into e power minus j omega t into dt. So that equal to, so integral, so 0 to infinite e power, so both are the exponential functions. So minus of a plus j omega into t into dt. So exponential function, that integration equal to e power minus a plus j omega into t by minus into a plus j omega. So substitute limits values. What are the limits? 0 to infinite. So x of j omega, so that equal to 1 by minus a plus j omega. So limit values. So substitute infinity, e power minus infinity, that equal to 0 minus e power 0 equal to 1. So here we are getting x of j omega equal to minus into minus plus, so that equal to 1 by a plus j omega. So here this x of t signal, it is a real signal. So this is the real signal. This is complex signal. It is what? Complex signal. So to draw the signal, we need to draw versus omega versus magnitude, omega versus angle. For that case, so drawing this one, first the magnitude of the signal, the magnitude of the signal. So magnitude of the signal is, so x of j omega, magnitude of the signal, that equal to 1 by under root of a square plus omega square. Then take the omega on x-axis, the corresponding that omega, we will get different magnitude values. And angle of x of j omega, so that equal to, we know that first angle tan inverse 0 by 1 0, and then denominator tan inverse of omega by a, we can write minus. So minus tan inverse omega by a. So this is the, for the magnitude, for this is for the phase signal. For that, so omega versus magnitude plot, this is phase plot, x of j omega magnitude plot. So at omega equal 0, at omega 0, this value equal to 1 by a. So maximum value. At omega equal to a, that value equal to a 1 by a square 1 by root 2a. And then you just draw the waveform, you will get like this. So at omega equal to a minus a, it will have the same magnitude. The magnitude equal to 1 by 1 by a root 2. 1 by a root 2. Here the magnitude equal to here, the maximum value equal to 1 by a. So this value equal to 1 by a. So this is the magnitude plot. So in case of the phase plot, phase versus frequency. So phase versus x of j omega versus omega. For omega equal to infinite. So here omega equal to infinite, the angle equal to minus 90. Minus 90. For the omega equal to minus infinite, the angle equal to pi by 2. So for the positive frequency, the magnitude equal to minus pi by 2. Minus pi by 2. For the negative, the magnitude equal to pi by 2. So it's infinite. It's the infinite. So it infinite. So it omega equal 0, the angle equal to 0 degrees. So this is this point and this point and this point. So at omega equal to minus infinite. So it minus, so this is a minus infinite. So this is a infinite value. So at minus infinite frequency, the angle equal to plus pi by 2. So this is like this. So this at omega equal to a. So at omega equal to a gets cancelled, tan inverse 1, the phase value equal to minus 44. A equal to at a, the magnitude. So this is the magnitude. How much? The magnitude pi by 4. Minus pi by 4. At minus a, substitute minus a gets cancelled. Minus 1, that equal to minus 1 gets cancelled. The angle equal to this. So this is the angle that equal to pi by 4. So this is the magnitude plot. So this is magnitude plot. So this is phase plot. Okay. If you get the signal in frequency domain that is complex, then we have to draw the magnitude plot and phase plot. For understanding only, we have drawn this magnitude plot, phase plot. It is not necessary for all signals. Just we need to find the Fourier transform and inverse Fourier transform. We go for the another problem. The second one. The second one. So second problem. So here the time domain signal, a period signal x of t equal to, so x of t equal to e power minus a mod of t. Here a is a positive. So how to draw the signal? First of all, we should know that signal. So in the signal sense system, for the any functions, which you can able to draw that signal. That you should learn how to draw what is the waveform, what is the signal in the graph. So this is x of t. So x of t versus t. For the positive values, see, I'm observing for the positive value. This positive value, the function is e power minus at. So exponential decay. And the negative values, for negative values also, negative values. So it becomes e power at. So for negative values, e power at, and e power at, after substituting t negative values, again that is also exponential decay. So this is the e power minus at. So this is e power at. For the positive or negative, the function is e power at. For the negative, automatically this is a decay. E power at, for the negative, it is a decay. E power 180 for positive, this is the decay signal. So it is about the time domain. So for that, so find the Fourier transform x of j omega is what? We know that formula x of j omega formula. So x of j omega equal to integral minus infinite to plus infinite x of t into e power minus jk omega naught into t. Sorry. So this is a Fourier transform. So omega into omega t into dt. So this given signal, it is having the magnitude for the positive and negative. So here I am splitting into the negative and positive. So that equal to, so minus infinite to the 0 x of t into e power minus j omega t dt. Sorry, dt plus, so 0 to infinite. So this x of t power minus j omega t into dt. So here the signal we can write like x of t. So this is for the e power minus at for t greater than 0. So this is e power at for t less than 0. So this is the case. For the within the for a negative, the signal x of t is e power at into e power minus j omega t into dt. So limits are minus infinite to 0 plus infinite, sorry, integration 0 to infinite x of t, the x of t for the positive, so that is e power minus at into e power minus j omega t into dt. So the x of j omega, so x of j omega that equal to integral minus infinite to 0 e power a minus j omega t is the common into dt plus integral 0 to infinite e power a plus j omega minus into t dt. So here minus t common, here t is a common. So now apply the integration. So you know the e power x integration, e power ax integration, e power x by a. So then e power the constant a minus j omega t by a minus j omega. Substitute limits. So limit equal to minus infinity to 0 plus e power a plus j omega by minus into a plus j omega. So limits 0 to infinity. So substitute 0, that is 1 minus, so 0 by a minus j omega plus 0 minus 1 by minus of a plus j omega. So minus minus gets cancelled. So what, 1 by a minus j omega plus 1 by a plus j omega. So take the common, then we will get, so a plus j omega plus a minus j omega. So a minus b into a plus b, that equal to a square minus b square. A square minus b square, j square, it gives a minus, minus minus then. So this is omega square. So this is, this gets cancelled. So in final step, so x of that j omega equal to, we're getting 2a by a square plus omega square. So 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 e power minus a mod t, its Fourier transform. So its Fourier transform, that equal to 2a by a square plus omega square. So this is a real signal, not complex. What we got in the previous, that is complex. So this is real. So this is about continuous time Fourier transform. So this is a concept. So we should remember this Fourier transform. It is used for the converting from the time domain to the frequency domain and frequency domain to the continuous time. For the aperiodic signal, the special case is the aperiodic. Fourier series, it is for the periodic signal. Then in next class, we will discuss some more problems and properties of the continuous time Fourier transform. Thank you.